We will be discussing 7.6 now, properties of solutions. We're essentially looking at what happens to the solution when you're adding the solute to it, which is the smaller of the two, remember. There's the solute and the solvent. The solute is the one of the smaller amount. And we're looking at how that changes the effects of the solvent. So solutions in general are transparent, meaning that you can actually see through them. They don't separate, meaning that if you sit them in a refrigerator or on the countertop, you're not going to see layers form. And they're really, really small ions or molecules that cannot be filtered. So if you pass it through a filter paper like a coffee filter, when you make coffee, the grinds actually stay in the coffee filter. These, however, would pass right through it. They also are so small, they're going to pass through a semi-permeable membrane. A semi-permeable membrane is it's like a clear coating, almost a piece of plastic, with holes so small that you can't see them. They have smaller holes than a filter paper. So sometimes a bigger particle can get stuck or move and not go through, whereas really, really small molecules like water can. In contrast, colloids have slightly bigger size, they're medium-sized. They still can't be filtered, they're still going to go right through a permeable filter paper. However, they will be separated by a semi-permeable membrane, which means that the water can go through it, but whatever's in there cannot, so it gets stuck on the other side. And then finally, we have suspensions, which are very large particles. And if you sit it out on the counter, they will make layers. Think of it as mud. If you have dirty water in a water bottle and you let it sit there, eventually the mud's going to settle to the bottom. Those particles are so big that they can be filtered, so you can separate them easily. If you just let it sit there, as I said, it's going to settle to the bottom. So that means you have to keep it stirring it. A couple examples would be like blood platelets. If you've ever seen someone get a blood transfusion, they've had to mix the bag before they give it to the person. And that's because of the fact that you'll start to see layers form if you let the blood sit there. Muddy water is an example that we just talked about. If you saw it in a plastic bottle, the mud would drop to the bottom. So here is a summary of the three parts: the solution, colloids, and suspensions. Notice that particles get bigger as you go down. Also, suspension is the only one that's going to settle out. They're also the only ones that are being filtered. So these are the three ways to separate it. You can't really separate a solution by trying to pass it through some kind of a membrane. You'd have to boil it or something. Semi-permeable membranes will separate the colloids, but the larger particles can be filtered. So if we go back, a mixture of the solute particles that do not settle but are too large to pass through a semi-permeable membrane. So they don't settle out, but they do go through they don't go through a semi-permeable membrane either. You can separate it that way. Colloids. Alright, so let's take a look at the properties themselves. It's all dependent on how much of the solute you have in there. The more of the solute you have, the more of an effect you're going to see. And we're going to look at things like freezing point and boiling point. We're just going to talk about them briefly. Freezing point actually lowers. So if we're talking about a solvent such as water, water freezes at 0 degrees Celsius, as you are well aware of. However, you may have noticed that in the wintertime, they sometimes put salt on the roads to prevent ice from forming. Well, that's all because of these properties that happens. What happens is when ice forms, we have water here. We had talked earlier about how the positives and the negatives are attracted to one another. And so when it actually forms ice, there's an attractive properties here. The oxygens and the hydrogens are attracted from other molecules with one another. And it forms a nice crystal. Well, when you have an ion in there or some other compound in there, what happens is if we put salt, that interrupts that formation of the attraction. So that means this oxygen will be more attracted to the sodium because of the fact that it has even more of a positive charge than the hydrogen does. Therefore, that interrupts that attraction. And the fact that it can't have that nice crystal now, it interrupts that crystal. It interrupts the way that things are attracted to one another. And so it forms more of a slushy than it does solid ice. Boiling point elevation is very similar. You're still going to have those positive and negatives in here that are interrupting, but instead of it boiling away, these negative and positive charges are so attracted to the water, it's pulling it down rather than, here is a beaker. Instead of the molecules drifting up as it boils, these molecules are now pulling the water back in because of that attraction. So the electrolytes that we talked about earlier in the chapter break up into ions. Then these ions get in the way of the positive and the negative interaction. So if we slip an ion in here, suddenly this attraction won't be as good. And that interruption makes it so that way the ice on the road doesn't freeze. From a biological standpoint, solutes are really important because of the osmosis process. If we look at this jar, we have sugar on this side, sucrose to be specific, and we have clean water on this side. Well, osmosis is the process of trying to get these two sides to be equal in concentration. So therefore, the water is going to leave this side and try to dilute the right side out. However, it's going to get to the point where the height of the water is going to start pushing down on the solvent. So it's a push and pull. It has to be evened out. So it's never going to get to the point where the right-hand side is as dilute as the left-hand side, because that's impossible. The left-hand side is pure water, where the right-hand side has little particles in it. So it's trying to get to the point where it is the same in osmotic pressure. As this becomes more dilute, it doesn't have as much of a drive to push from left to right. And then the fact that gravity is acting upon it too is pushing it down, and it's pushing it back. So once those two pressures equal out, that's when the concentration stays the same. The level of the solution starts to rise because that water dilutes the solution. It will not necessarily become equal over time. It could, depending on the concentrations on both sides, but that osmotic pressure is what's going to be becoming equal. Now, this actually has a really important value as far as biological substances because of the red blood cells. Remember the semi-permeable membranes. Permeable means that it can break through. Semi means it can break through a little bit. It can be some particles can go through and some cannot. Meaning actually water specifically, because we need to make sure that those pressures are the same. The amount of solute on both sides has to be as equal as possible, otherwise you're going to have issues in the red blood cells. So it's that pressure, not necessarily what it is, but the pressure of what it is. The amount of ions that are there. If it does change, it's going to cause damage. For instance, isotonic solution. That's the key term that you need to know. Isotonic solution is one that the solution that in the IV that you add to somebody's bloodstream is the exact same pressure as the blood cell itself, the red blood cell itself. So for instance, 5% by mass of glucose has the same pressure as the red blood cells. That means when you put a red blood cell into the solution, the osmosis that occurs is just going to be an exchange. There's not going to be any form of one side gets more solution than the other. One side is not going to get more water than the other. Whereas if we go to hypotonic solution, another key term here, hypo means lower. So it's a lower concentration, which means that since it's a higher concentration in the cell itself, the water is going to go into the cell. When that happens, the cell is going to expand and expand and expand until it gets to the point where it explodes. It's going to swell and burst. That's called hemolysis. Hypertonic means a higher. That means instead of the water going in, now the water is coming out and it's shrinking up. That's called crenation, when it shrinks in size because the water that's inside these cells are actually escaping into the solution because it's trying to even out that osmotic pressure. So here's the summary. Here's the three cells. This one is normal because it's in an isotonic solution. This one's in hypo, which means that it's lower concentration. That means that the water is trying to go into the cell, and the cell ends up bursting. And then this is a hypertonic, meaning a high concentration. The water is coming out of the cell and going into the water. Either one of these situations are bad. Now, dialysis is a way to do this artificially. The solvent and the solute pass through the artificial membrane, which is like a big piece of plastic that only really tiny particles can go through. The large particles stay inside. But this is a way for somebody, for instance, somebody who needs kidney issues, who has kidney issues, to remove bad things from the blood. So that way they can stay healthy. And that is the end of section 6 and chapter 7 in general.